Hi, I'm Jack Baker. In this video, I'm going to provide an introduction to the CEE 204 class, Structural Reliability. My goal in the next few minutes is to talk over, kind of from a big picture perspective, what are the types of problems we're trying to solve in this class? Generally, what is the methodology going to look like? What are our strategies going to be for trying to solve that problem? And give you a little bit of a sense of the scope of the course so that you can kind of understand what you're getting into. And those of you trying to decide whether to take this course, you can decide whether this is a course for you or not. Okay, so the motivation here is that, as engineers, we're studying very complex systems. So I've put a couple figures up here to look at just to think about the complexity. So whether this be kind of in the upper left, large industrial facilities like nuclear power plants, in the lower left, a building that we might design to resist various types of loads, or on the right, a distributed infrastructure system. So this is a map of the major roads in the San Francisco Bay Area. And what these systems have in common is that they're made up of many components, whether it be kind of physical components like beams and columns in a building, or larger components like a bridge that's part of a road network. And those components have uncertainties associated with their performance under loading. The loading also has uncertainties. And the relationship between loading and component properties and the failure of this overall system, however we define failure, that can be a complex relationship. And further, these systems are generally quite reliable. It's very rare to have failures, but we do have failures occasionally, unfortunately. And the question is, how do we assess kind of the probability of that failure when the system is complex and there's many sources of uncertainty? That's the type of problem we're going to be studying in this class. So to maybe be a little bit more precise in some examples, let me talk you through a couple examples of this. So one problem we study a lot at Stanford in the research side of things here is the collapse capacity of a building. So here's just kind of some simple diagrams. On the left is a 2D picture of a frame in a building, and these little red arrows are denoting that the beams and the columns, or the beam-column connections specifically, we anticipate seeing nonlinear behavior in those elements under earthquake loading. And so over on the right is a diagram of what the loading versus the displacement of one of those members might look like under large demands produced by an earthquake. But the behavior of those beams and columns under loading has some uncertainty associated with it. So here to elaborate a little bit more, here's a diagram of that behavior of a component blown up a little bit more. So now slightly different units. The horizontal axis is the rotation of one of these elements as it's bent, and the vertical axis is the moment at the base here for a column element. So as you increase the moment, how much does that element rotate? And in red is shown what we call a backbone curve. So this is a force displacement curve that, as we start from kind of zero moment, it increases up in a linear manner. At some point, the linear behavior stops due to damage on-site in the element, and the rotations can continue if you continue applying forces, but with a reduced stiffness indicating the presence of damage. At some point, we even get into this descending backbone section of the element where, as the chord rotations get larger, the moment being resisted actually is decreasing, associated with severe deterioration. So that would be if we kind of push this element in one direction, we get this backbone curve. As we cycle the element back and forth, the cyclic loading will also cause deterioration. And so we see in blue these cycles back and forth showing kind of smaller base moments for a given chord rotation, indicating cyclic accumulation of damage. So we can build models like this in the computer, and there's several parameters associated with the behavior of a model like this. And each of those parameters is, in principle, uncertain. So one parameter would be what we call this plastic rotation capacity. So how far can we rotate out before we get to this negative slope branch? There's a lot of uncertainty in that. That's kind of a complex set of damage that occurs to create this negative sloped portion of the backbone. And so it's difficult to predict for a given specimen when that's going to onset, and so we would have some uncertainty. We could represent that by a random variable. Similarly, so let the slide advance. We have uncertainty in this stiffness, the slope of this descending branch. We call the post-capping stiffness. We have uncertainty in member strength. What's the base moment at which all this nonlinear behavior starts to occur? We have uncertainty in this initial stiffness, so how stiff is the member even in the elastic range? That's a parameter we have to estimate. And we have uncertainty in the stiffness after the element yields. And finally, this cyclic behavior, as the element's deteriorating over multiple cycles, there's a parameter in there that controls how fast that happens, how many cycles it takes to see a given level of deterioration. So there's another random variable. Okay, so we have all these uncertain parameters. And then if we think about this back to our building model in the lower figure here in the center, every one of these beam column connections is potentially subject to this type of deterioration. So in a reasonable sized building, we're going to see dozens or perhaps hundreds of these types of elements that we have to model. And each one of those elements has a number of uncertain parameters. So the question is kind of, if all those parameters are uncertain and they ultimately affect the behavior of my building, how do I propagate that uncertainty to understand the likelihood of failure of my building? The other constraint here is that my structural models generally take a non-inconsequential amount of time to analyze, even if it takes a few minutes to analyze one of these buildings under an earthquake load. I can't just try every combination of every random variable and kind of brute force my way through this problem always, because I might end up with kind of a prohibitive amount of time that would take to analyze. And so I want to think about being intelligent of how can I learn about the role of those parameters, uncertainties in the safety of my building. Another example that we can think of at a different spatial scale is this transportation network. So here's a kind of a high-level diagram from some analysis from Mahalia Miller, a recent PhD student from Stanford. And she was looking at risk to transportation networks, road networks. So here, if we think about what's uncertain in this problem, so over on the far left, we have a map of ground shaking intensity from an earthquake scenario with warmer colors indicating stronger ground shaking intensity for this scenario. The second panel is showing, in the small dots, show the locations of all the bridges in this road network. The red dots indicating damaged bridges and the open dots indicating undamaged bridges. And those would be damage caused by this earthquake shaking. The third panel then is results of analysis to say, well, if some of those bridges are damaged, how is the traffic going to flow through this transportation network, considering damaged and potentially closed bridges? So some of the traffic is going to have to reroute. There will be congestion. There will be changes in people trying to use the network. So we'll have kind of the impacts there. And then ultimately, those travel time impacts are going to relate to impacts on users in terms of loss of availability of their transportation system for accomplishing what they want to get done each day. So each one of these panels is associated with uncertainty, right? We have uncertainty in the ground motion shaking intensity we might see in the future, uncertainty in the occurrence of damage to bridges, uncertainty in the impacts on the transportation network, and uncertainty on impacts to individuals. So again, we have lots of uncertainties to consider. We have computational challenges in terms of getting all this analysis done. And we want to think intelligently about how can we assess the probabilities of bad outcomes in a complicated network like this. Okay, so thinking about those as motivating problems, let's return to this course. So we're thinking about the kind of safety of structures with regard to some sort of failure. And we're going to consider explicitly that we have uncertainties, right? Pretending that there's no uncertainties in these problems is not a productive strategy in general. So what we're going to do is we're going to try to think about the probability of failure of one of these systems. And we're going to talk about probabilities of failure so often that we'll abbreviate that to P subscript F. And the systems we're going to think about in particular in here is we want to think about systems with many sources of uncertainty, which in terms of our calculation approach, that means there's going to be many random variables, as we'll use random variables to represent uncertainties in our problems. So we want to think, in class we'll focus a lot on problems with kind of 2 or 3 or 4 or 5 random variables, but we want to think about the scaling of these solution algorithms to real world problems where there might be hundreds or thousands of random variables associated with a problem. The other, so that's backing up for just a second on that point. So that differentiates us a little bit from the 203 class where we were oftentimes thinking about 1 or maybe 2 random variables at a time. Here we're going to think about kind of greater numbers of random variables, and that'll have some impacts on the strategies we can use for our analysis. The second defining feature of the problems we're going to study in here is that in general our systems we study are pretty safe, which means that PF is a very small number typically. Our P back up here. Okay, so the probability of failure is very small, right? Most of the time our buildings aren't falling down, our industrial facilities aren't having accidents. And so that has important implications here in terms of our analysis, because it means we're going to be out in the tails of these probability distributions. We'll elaborate later. But the typical values that these random variables take are not going to be associated with failure. And so we're thinking about kind of, what's the bad luck situation where we have kind of a low capacity of a component and we have a high, unusually high load on the structure that might cause a failure. We're interested in the tails of the distributions. That's both going to kind of increase, or cause complexities in some of our analysis, but it's also going to motivate the types of solution strategies we use, because we want solution strategies that are effective when thinking about tails of distributions. All right, so we're trying to find probabilities of failure of these systems. Then the question is, what is a failure? And really, it's going to be our definition, some sort of what we'll call a limit state, some sort of state of the system we're studying that we're going to define as an adverse outcome. All right, so that could be things like collapse of a system, so collapse of a building under earthquake shaking, failure via fracture or global instability, something like that. But it need not be kind of the system we're studying kind of reduced to rubble on the ground. It could be a serviceability failure. So it could be something like excessive deformations or occurrence of vibrations that are unacceptable. Or it could be kind of an economic limit state. So it could be what's an outcome where the costs to repair the system or the cost associated with the impacts of this outcome are greater than some threshold. So in performance-based engineering, for example, we're trying to assess financial losses. We might think about a cost-related limit state. So, and to generalize even further, typically we're interested in adverse outcomes. So something bad happened, and we want to know what's the probability of something bad happening. But it need not even be something bad, right? So we'll use failure typically to indicate that it's a bad outcome, but perhaps there's some unusually good outcome that we're interested in as well. And we could use the same algorithms to study that in general. Okay, so to solve this problem, there's going to be this equation up top is kind of the general form of the equation that we're going to focus on mostly here this quarter. And I'm going to flash it here once. We'll obviously spend some time on it as the quarter goes on. But let me highlight some components of this analysis. So we're going to say over on the left here, PF, the probability of failure of the system, is the probability of something. Now what we're doing here is I've got this function g of x. So g, and I'll just leave the argument blank, is, some function that indicates failure when g of x is less than 0. So this is going to be some function, and if I plug in the values of these inputs x, the function will tell me whether I have a failure or not. Okay? And this function could either be an equation, or it could be an outcome or an output from a computer analysis or something like that. Okay, and this x that's input into here is going to be a vector of random variables. So those are going to be random variables describing everything that's uncertain in my problem. So in my equations here, I'm going to use boldface to indicate vector values. And then when I write with my pen, I'm going to use an underline to make up for boldface. So I've got this bold vector x, that's all my random variables. And so I will specify probability distributions for those, and then I'll use this function to decide whether a particular realization of the values of those random variables indicates failure. Okay? So probability of this function being less than or equal to 0 will be the probability of failure. And then how am I going to evaluate that? So what I'm going to do is I'm going to have over here on the right side, and here we'll see some of our old probability notation. So I have a probability density function for this random variable vector x. Okay, so for all these random variables, I'm going to specify this joint probability density function. And then I'm going to integrate that probability density function. And remember, the limits that I integrate over will tell me the probability of the random variables taking the values within that limits of integration. So what I'm going to do is I'm going to integrate over the limits such that g of x is less than or equal to 0. So what the right-hand side is doing in words is saying, what are, the probability density function is telling me what are the probability densities of any realizations of these random variable x's. And I'm going to add up those probability densities via this integral over the domain of values of these random variables that are associated with failures. Right? So that's what this limits of integration is. So for all the possible values of x causing a failure, what's the probability density associated with that? And that'll tell me the probability of failure. Okay, so that's kind of our general strategy and a general formulation of the problem. So why can't we just solve this problem today and be done with the class? So it's the typical things that, typical issues we face are numbered here down below, and perhaps you've read ahead already. So first of all, we've got to specify this joint probability density function for x. Sometimes that's hard to do. Sometimes we don't have enough information. Sometimes it's kind of a hassle to work with this joint probability density function. So we're actually going to consider kind of shortcut calculations to this problem where maybe we don't have to specify the complete joint density function just for convenience sake. We'll end up with an approximate answer, but it would be a appropriate level of approximation given the available information. Okay, second limitation is that this limit state function, that's what we're going to call this G function, because it's telling me whether I fall into a given limit state or not. That limit state function might be difficult to evaluate. For example, it might be the output of a big expensive computer analysis. So the reason that causes challenges is that if I want to integrate over this domain where g of x is less than or equal to 0, just figuring out what that domain is can be computationally a problem. And so that's going to limit us in some situations. Okay, and then third, even if those first two problems don't exist, even if I know my complete probability density function, and even if I can evaluate this limit state function, this integral can be high dimensional. Right? And numerically evaluating a high dimensional integral is problematic. And I should note, basically never can we evaluate this integral analytically. We're almost always going to be evaluating it numerically. And when n, the dimension of x, gets greater than 2, so once I have kind of 3 or 4 or 5 random variables, doing a kind of numerical quadrature integration in those high dimensions is quite hard. And once I've got more than on the order of 5 random variables, basically I can't do that numerical integral just via brute force. And so we've got to think about kind of effective numerical strategies for evaluating this integral in high dimensions, because the high dimensional problem is the interesting one, as we noted just a moment ago. Okay, so with that as kind of the problem we want to solve and some of the challenges we're going to have to overcome this quarter, let's talk a little bit about, even if we could, solve this problem, kind of what are some inputs, what are some benefits of this calculation, things like that. All right, so if just thinking generally about probabilistic modeling, which incorporates the modeling of the type here, there's kind of two aspects to the problem. Right, so one aspect is we have to describe random phenomena. Okay, so that means basically specifying probability distributions for random variables. That's a topic that we spent some time on in CEE 203. We're going to spend very little time in this course dealing with this. We're not going to work very heavily from kind of empirical data trying to build these models for random phenomena. Generally, we're going to take them as specified here and think about how to utilize them to solve the problems we're interested in, which just brings us to our second part of the problem, which is to study functions of these random phenomena once they're known. And that's going to be our main focus in this class. All right, so we'll take some random variable models as given and then say, I've got this function of these random variables, specifically a function that tells me whether my system failed or not, and I want to try to evaluate those functions given my pre-specified random variable models. Okay, and let's assume we can solve this problem eventually once we've got some strategies to deal with that integral from the previous slide. So some things we're going to think about. So one is, let's just compute the probability of failure of a structure or a system. So that number is of interest to us in general to decide if that performance is acceptable. In particular, we can compare those probabilities to other sources of risk and ask, is this failure of this system under this loading condition that I'm thinking about so high that I should be concerned about it and try to avoid it, or is it in line with other sources of risk that I might face, or that the occupants of this structure might face, or the users of this structure might face. We can think about decision making of that type then. So we can start saying, how should I design a system, thinking about kind of higher design standards being more expensive, but also producing benefits in terms of safety. Right? I need to know both kind of the costs and the benefits to make those types of decisions, and these analyses would help support that. We can also make decisions about things like inspections to say, well, if the state of my system is has a lot of uncertainty, and I could do some inspection to reduce that uncertainty, but I would have some cost associated with that inspection. Is it worth the time or the effort to do those inspections in terms of supporting decision making about ensuring satisfactory performance of the structure? Okay. We'll also use these types of calculations to calibrate building codes, right? So building codes have lots of rules and parameters and things in them, and you're generally not evaluating integrals relating to probabilities when you're using a building code, but a lot of those rules are calibrated via calculations of the type that we'll develop in this class. And so we're going to talk about the relationship of these calculations to calibrated building codes and how would one calibrate a building code using these types of calculations. Okay, and then the fourth item on this list here is understand how the model assumptions impact our safety analyses, and in particular, kind of how sensitive are our safety calculations to particular inputs, or how is uncertainty in particular random variables driving the potential failure of my system. And so thinking back maybe to that building model, the building collapse under earthquake loading, of those 6 different parameters I showed in the animations, which of them is most important in terms of a bad outcome of that parameter leading to bad performance of the building. So we want to understand sensitivity, both so that we can refine the inputs for the most important random variables, and perhaps we can also ignore some of the random variables that just don't make any difference in order to simplify our problem and devote our resources where they have the most, provide the most insights. Okay, so we'll talk in this class. We're gonna do kind of calculations and develop the tools for performing these calculations. Then we'll also use those calculations to try to make decisions in some example applications. So those will be the types of problems we're trying to solve here in this class. Okay, a couple slides here to just put us in context. So this general field of structural reliability calculations is not an ancient one. It's reached maturity just in the past few decades. And just to give you a sense of timeline, here's kind of some key dates in the development and use of these tools. So it was the 1950s where people first started trying to link mathematical probability with strengths and failures of systems and things like that. So probability has been around for longer than the 1950s. It's been around for a couple centuries in a formal sense, but it was not tried to be linked to kind of probability of failure type calculations until middle of the last century. In the 1960s, people started thinking about kind of algorithms specifically devoted towards these reliability calculations. If I want to find the probability of failure of something under these circumstances where I've got kind of more than one random variable and it's a low probability of failure, those kind of reliability specific algorithms were getting developed in the 1960s. And then really importantly, in 1967, Alan Cornell, who we'll talk about a lot through this class, he wrote a seminal paper arguing that we could use one of these algorithms, particularly the second moment method algorithm we'll talk about later, which is a way of getting at these structural reliabilities, and we could use it to calibrate building codes. So this was a transition away from, say, kind of a pure factor of safety type calculation to say, well, why don't we build these building codes so that they're achieving some target level of reliability? And there was a number of advantages relative to past strategies that made this a really compelling argument. So, this is on the order of 50 years ago that this proposal was made. So it was received a lot of attention and a lot of acceptance for its potential. And that motivated then in the 1970s to say, well, if we're going to use this strategy, we need to characterize all our random variables that go into structural failures. So let's go collect data about the statistical properties of loads and the statistical properties of material strengths and so on, so that we can do this code calibration. All right. Another key seminal activity was in 1975. There was this important study. It was called WASH 1400. You'll hear that thrown around occasionally in the structural reliability community. And this was a study of a nuclear reactor and its safety and its viability for operation. And here they struggled because, until issuing this report, with having to face these uncertainties. So nobody believed that the reactor was perfectly safe, but on the other hand, they wanted the reactor to be extremely safe and have probability of failure very close to zero. And so how do you go about assessing kind of satisfactory performance of this reactor? And so they used formal reliability methods to do the safety study, which was the first time in kind of one of these highly technical industrial applications that kind of reliability methods were used to establish acceptable performance of the system. All right, around the same time, the U.S. Geological Survey, it's a U.S. government agency that produces maps of geologic hazards. So they produce the map of seismic hazards that we use for are establishing earthquake loads when you design buildings in the United States. So they built a probabilistic map basically describing probability distributions of loads, which is then used in building codes and things like that. That was kind of a key step in characterizing loads in a statistical sense. Then in 1980, the National Institute of Building Standards released the first building code calibration, or first building code that was calibrated using these probability-based methods following Cornell's suggestion. So here now we've converted to this reliability-based building code in 1980. 1986, the American Institute of Steel Construction released their load and resistance factor design manual. And these load factors and resistance factors, which presumably many of you are familiar with, those are all calibrated using probability-based studies of the type we'll think about in here. AASHTO, which regulates design of bridges and highways in the United States, they released a manual similarly a few years later. And these approaches got quite popular in the 1990s. So we've now had a few decades of dealing with those designs, but the AISC and AASHTO manuals were really focused on individual components. So how do I design a beam inside of a building? They weren't really thinking about the building level safety, the system level safety, so to speak. And kind of an interesting development in that front was just a few years ago, this FEMA P695 study. Here they were calibrating R factors along with other factors that are kind of building level factors for seismic design using kind of system level assessment. So assessing the entire building and thinking about things like those parameter uncertainties that I spoke about in the first few slides of this presentation. So the point here is that this isn't kind of a centuries old field. It's decades old, and there are kind of important developments still ongoing kind of as we speak. So it is an active and alive field as well, which is why we make this course part of our graduate curriculum here at Stanford. Okay, final slide for this presentation. So we're going to, as we work through this quarter here, we're going to think about various strategies for solving that integral. So this integral over g of x less than or equal to 0. And we're going to use different strategies depending on kind of what our objectives are of analysis, how much information we have, and how much effort we want to go into our solution. And I'll just highlight a couple things here in this table. We've got kind of over on the left level 1, level 2, level 3 methods, going from kind of very simplified up to a quote exact methods down at the bottom. And these different methods are going to make different types of assumptions. There's going to be different methods for calculating our failure probabilities, different levels of precision in how we characterize probability distributions. That g of x function will turn out to be pretty important, in particular whether it's a linear function of those random variables x or a nonlinear function of those random variables. So linear functions are much easier to deal with. So some of these top rows, we have kind of strategies that are dealing with linear limit state functions or approximate a nonlinear function as linear, which can sometimes be a good approximation. And then finally, the final column is dealing with the result. So kind of our more exact methods, we can think about failure probabilities, which is our kind of ultimate goal here. In the middle, we've got, I'll call it nominal failure probability. So we're getting in that neighborhood, but not quite the right answer. And up at the top, we've got kind of more limited sets of outputs. And we don't get it those failure probabilities due to the approximations we make. Okay, so this will be a table that we'll pull up throughout the class as we dig into these different methods. And one of the goals will be to kind of learn these different solution methods, learn their relative advantages and disadvantages, so that you're able to kind of appropriately choose an algorithm and method for solving these problems as you face a new problem out in the real world. Okay, so I'm going to stop here in terms of the introductory slides, but I hope that gives you a flavor of the types of problems we'll be solving in this class. The general, both kind of the big picture motivating problems as well as the general solution strategies we'll try to employ. And of course, moving forward in the next few weeks, we're going to dig in detail to these different solution strategies and dig into that reliability integral and think through more deeply the challenges as well as the strategies for overcoming those challenges when we're trying to do our assessments. Okay, so I hope that's been a good introductory video for you all, and I look forward to seeing you in class here in the near future. Bye.